In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 4, Constitutive Relations, Part 2. In this part, we are going to consider a problem, an example which we are going to solve. This is our problem or example. We have a plane strain compression of a thick block. That's a block of material. As you can see, the width and thickness have dimensions near to each other, and they are relatively thick, so that this is not a thin block. This is not a thin sheet or something. It's a block. And says that it is under plane strain compression. So how is it that it's under plane strain compression? First of all, it says it's subjected to an increasing pressure sigma xx equal to minus p. So p is the pressure on the sides, and it's increasing from 0 upwards. Because it's compression, it is shown by negative sign. So we have these rigid walls in here, so that the block cannot move in that direction, in the lengthwise direction. In fact, x, y, z are in these orientations. So we have p in the x direction, and in the z direction the block is restricted from moving by these rigid walls. Therefore we have no strain in the z direction. And we only have sigma in this direction, but because the material is free to move in the y direction, we don't have any stresses in the y direction. But because it's restricted from moving in the z direction, therefore we must have a stress in the z direction as well. Therefore we have in two directions, x and z, we have stresses. So that's why we say it's a plane strain, because we have restricted it from moving in one direction, and we have only it can only move in two directions, that is in x direction and y direction. That is the problem. So we have sigma x equal to minus p, epsilon z is equal to 0, and sigma y is equal to 0. What do we want? We want to do an analysis, an elastic plastic analysis of this problem. Elastic plastic analysis of the problem means that as the pressure increases, it goes through the plastic region, because we are saying that increasing pressure. So it's increasing from 0, it goes to elastic region, and as we increase the pressure, it goes to plastic region, and then as we increase further this pressure, the material goes through yielding. So we want to have an analysis of elastic plastic nature. We want an elastic plastic analysis. It means that we want to derive the equations for the elastic part, for the plastic part, and for the yield condition. We call it incipient yielding, the start of the yielding. After yielding, we are not interested how it is changed, the shape is changed or whatever. That is another area. Here in engineering plasticity, so far we are interested in the elastic region, plastic region, and incipient yielding, which is the start of the yielding, where the stress tensor reaches the yield surface. The solution to the elastic problem, the elastic behavior of this problem, first of all, we present that, the solution to the elastic problem. Now we use the elastic equations that we introduced in the Prandtl-Ross equations. The elastic part are these equations. We substitute for the values that we have for these strains and stresses. For instance, for this expression, we know that the strain in the z direction is 0 because we have no deformation in the z direction, no material flow, because we have put these rigid walls preventing the material to flow in the z direction. So deformation is 0. What about sigma zz? Obviously, because the material is hindered from moving in the z direction, there must be some stresses in the z direction. And sigma xx, we have said that is equal to a compressive pressure P, which is shown here by minus sign, and sigma yy also is 0 because the material is free to move. Okay, so if there is a stress in the y direction, it causes a movement of the material, a plastic deformation, and the stress is relieved. So there is no stress. Stress is 0. And from here, everything is known, and we get sigma zz equal to minus mu p. Similarly, in the first relationship, we could substitute for sigma xx again is minus p, sigma yy is 0, and sigma zz which we have just obtained here. So if we put all these values, we get the strain increment in the x direction, and integrating we get the strain in the x direction, and also a strain in the y direction. We substitute for sigma yy equal to 0, sigma x is minus p, and sigma z also is minus mu p. Therefore we get epsilon xx is minus p over e, 1 minus mu squared, and epsilon yy is equal to p over e, mu times 1 plus mu. That is the elastic analysis. Okay, we have obtained all the stresses and all the strains in the elastic behavior of this problem. Okay then, so we've done the elastic part, which was this part. Now we go to the plastic part. We use the Prandtl-Ross equations for the plastic part. And we have here the epsilon xx is equal to 1 over e d sigma xx minus mu d sigma zz, because the sigma yy is 0, and similarly here sigma yy is 0. So we just substitute for these values, and we get now, in order to go further, because in the plastic part we want to know, if you remember, the problem said that the pressure P is applied as increased. Okay, so pressure P is increasing from 0 to where the material yields. So we need a yield criteria to solve the problem, according to which yield criteria you want to solve it. So we use the Tresca yield criteria. Supposing this material obeys the Tresca yield criteria, that's why we call it the Tresca material. Now, take now the Tresca yield criterion, which states that yield occurs when sigma yy is equal to minus y. That means that P reaches this number y, where y is the uniaxial yield stress in compression. Assume further perfect plasticity. Now, here we have assumed perfect plasticity. It means that once we reach the yield point, then the stress does not increase anymore, and the material deforms accordingly. So if we assume that, then sigma x is equal to minus 1 holds during all subsequent plastic flow. Thus, with d sigma x equal to 0 and the epsilon zz equal to 0, we could use this equation to solve the problem for the plastic analysis. Okay, I should mention that here we have assumed an elastic, perfectly plastic material. But if after yielding the stress increases, that means the material is strain hardening, work hardening, and we could use proper work hardening model for that. Now, we are not doing that here. We are just using the yield condition and this number alone. So we don't have any strain hardening. Now in here, we substitute for sigma xx equal to minus y. Therefore, d sigma xx equal to 0 because that's a constant. So in here, d sigma xx is equal to 0. We have 1 over e times minus mu, so we get minus mu over e d sigma zz. And in here we have put minus y, so if we bring out the minus sign, we get 2 over 3 d lambda y plus 1 over 2 sigma zz, because that's minus, it's minus, it becomes minus. And for the second equation, this one, the epsilon y, we have again this sigma xx, which is 0 because sigma xx is a constant, y minus y, and therefore here we get minus mu over e d sigma zz like that. And in here we put for sigma x is equal to minus y, so minus times minus is plus 1/3 of d lambda y minus sigma zz, because that's minus sigma zz. And for the third equation, this sigma zz is 0 because in the z direction we don't have any deformation. So 1 over e, here we get this sigma zz, again here minus y, that becomes 0, 2 over 30 lambda minus y times minus is plus, so half y positive and plus sigma zz. So these are the equations that we get, and I have written it here again for the epsilon xx, y, and the epsilon z, of course, is 0. And therefore, from the last equation here, I can obtain the lambda. Okay, that's the lambda. Rearrange it, we get this one. And I substitute for d lambda in here. Okay, so put this in there and there. So I get this equation. That's how we obtain d lambda in this sort of problems. If you remember, that was the instantaneous constant or plastic multiplier. And also for d lambda, I substitute here. Therefore, I get these two equations. If you look at it carefully, we have here the epsilon xx, sigma zz, sigma zz, sigma d sigma zz. Okay, so we have sigma zz and epsilon xx and epsilon y, and again everything in terms of sigma z. Other things are known. So we have these two equations which we can integrate. Okay, we can integrate these equations using this integration law, and also the boundary conditions are this sigma x minus p. Of course, we don't need that. We don't need this sigma y is 0. We don't need this. Only this one, p is equal to y, and sigma zz is equal to minus mu p. So we can solve these integrations like that. Okay, so we get epsilon xx equal to that, and epsilon yy equal to that. So we have obtained an equation of strain in terms of stress. Okay, and we could so this is the plastic behavior, and we have analyzed it, and so this is the analysis of this problem for elastic and plastic parts, right? And we can draw these sigma zz over y and e over y epsilon for different values of sigma zz. We usually normalize because it is easier, it's dimensionless, so e over y is normalized, sigma zz over y, and as you can see, this epsilon yy and epsilon xx, the variations are like this, and this is the elastic part. Okay, these are the elastic part, and these are the plastic part. As you see, we approach this value. Half is the limit of this problem, and these are the strains that we get. As you can see, epsilon yy and epsilon xx approach each other as we continue the deformation. Okay, these values, of course, the value of mu in here is 0.3 or 1 over 3, because mu is the Poisson ratio, and in the elastic range it is 1 over 3, and for the plastic, of course, it's half, which we used it before. So this half, in fact, is mu for the plastic part, but for the elastic part, we put for the metals usually is 1 over 3 or 0.3. So that's what we have obtained. That's what is showing here. Mu is 0.3, and the multiplication of these, of course, will be some numbers here.